Sorry about that. Okay, lecture four. Uh, the lecture today is going to hopefully finish talking about locally convex spaces, and then the next lecture will start with talking about calculus and locally convex spaces. Okay, let me get my Zoom set up. If you have any questions that you want to ask while I'm getting set up here, let me know. Okay, good. Um, okay, good. Without further ado, let's get started. Um, okay, so I think last time we came to a reasonably good picture of how you should think about locally convex spaces with a couple examples that we talked about. And so today I want to sort of fill in basically things that you can talk about with locally convex spaces, okay? Um, So first, let's talk about some elementary kind of topological properties of locally convex spaces. So we'll start by recalling a definition from just topology. So if we have a topological space, okay, and okay, so it is Hausdorff. So there's the property of Hausdorff, and if you've seen it before, good. If you haven't, well, here you go. It's Hausdorff if given x1 and x2 in S distinct, there exists neighborhoods n1 of x1 and n2 of x2 such that n1 intersect n2 are empty. Okay, so the way you say that normally is you say that distinct points have disjoint neighborhoods. Okay, so the picture of a Hausdorff space is if you have distinct points, I can find so x1, x2. Okay. And there are examples of non-Hausdorff spaces. Okay. And we've seen one. Well, essentially we've seen one. So if you just take, if you hear some tapping, that's coming from above me, and it's a dog. Okay, so we're going to take R2 and we're going to take its topology, not the standard topology. We're going to take the topology defined by the single seminorm. P1, which takes a point x1, x2, and R2, and just gives you the absolute value of x1. Okay. So what do open open sets look like there? Well, a base for the open sets consists of vertical strips. So we saw this last time. Okay, so open sets. So a base for the topology are open vertical strips. Okay, so things that look like this. Okay, so that's an open set. All right, so the fact is, if you take any 2 points, which are on the same vertical line, say a point here, and a point here, there will not be a disjoint neighborhood of those 2 points because any neighborhood of, say, this point will consist of a vertical strip which contains that point, and that same vertical strip is also, of course, going to contain the other point. So there's no way of finding disjoint neighborhoods. Okay. All right. So that's Hausdorff. And we're going to assumption. So let me say something about Hausdorff if you haven't seen it, or maybe I'll say something that may even be interesting if you have seen it. Um, uh, generally speaking, one regards topological spaces that are not Hausdorff as being pathological. That being said, the Hausdorff topologies do arise in natural ways. Sometimes you can start with Hausdorff topologies and undergo some things and end up with a non-Hausdorff topology. In algebraic geometry, the Zariski topology is not Hausdorff. So there's all kinds of reasons why you might want to talk about non-Hausdorff topologies. But in this course, we're going to assume topologies are all Hausdorff. So if I don't say anything about a topology, you can assume it's Hausdorff. Right. So in the course text, I've tried to be careful about that and said Hausdorff whenever I need Hausdorff to be true. I hope I probably have omitted it sometimes when I needed it, and I'll try to catch those if I see them. And if you see a place where I don't say Hausdorff, ask me if I meant to. Or you can just assume that everything's Hausdorff and your life will probably not go too far awry. Okay, so all topological spaces are going to be Hausdorff. Just so I don't have to write Hausdorff all the time. And for a lot of the constructions that we're going to do later on, Hausdorff is essential. Okay. And if you want to see discussions of things like Hausdorff properties of spaces, you can look at the topology notes that I've uploaded as sort of supplementary material for the course. There's a section on sort of what are called separation axioms, of which Hausdorffness is one. So you can read there and see the whole, well, not even the whole spectrum, part of the spectrum of separation axioms. Okay. Okay, good. So let's maybe see what are the consequences of what it means to be Hausdorff for a locally convex space. So let V O be an LCS. Okay, and here, just for a moment, because I want to say what Hausdorffness means for LCSs. I'll say that it's not necessarily Hausdorff. With P, a generating set of seminorms, as we talked about last time. Okay, then it's an easy thing to check that the topology O is Hausdorff if and only if given a non-zero vector V, there exists a seminorm such that P of V is not equal to 0. Okay, so there's some seminorm which evaluates to something non-zero on every non-zero vector. Okay. So let's suppose that VO is not Hausdorff. And what I want to, and this is not a necessarily important thing to say at this point, but I think it gives a bit of geometric insight into how locally convex topologies work. So I'll talk about it. So V is not Hausdorff. Then if P is one of these generating set of seminorms, then in fact, for any seminorm, you can verify that P inverse of 0, okay, so all the vectors whose seminorm is 0, this is the subspace. Okay, that's very easy to see. You need to check that it's closed under addition and scalar multiplication. Scalar multiplication follows from the homogeneity property of the seminorm, and closed under vector addition follows from the triangle inequality. Okay. All right, so then we have the subspace. Okay, so somehow in the Hausdorffness is characterized by the existence of a seminorm for every non-zero vector, the existence of a seminorm which evaluates to something non-zero. Okay, so what I'm going to do is I'm going to take the subspace of the intersection of all of these subspaces on which a seminorm P vanishes. Okay, so this is going to be so an intersection of subspaces is a subspace. So this will be a subspace. So this is the subspace where all seminorms vanish. Okay, and if it's Hausdorff, and so this thing is equal to just the zero subspace if it's Hausdorff. Okay. All right. And so if you want to build, then define, sorry, define, and let's call this thing n. Let's just call it n. All right. So actually, let me call it z for 0. Okay. So what I can do then is I can take V and I can quotient it, just algebraically quotient it by the subspace Z. Okay, so that's just going to be some vector space now. Okay, um, um, and sorry, and given a seminorm P in P, define P0 to be a seminorm on V naught. Okay, so it's going to be a seminorm on V naught. So I need to tell you what it does to a vector in this quotient. Okay, but every vector in this quotient you write as, it's a coset. So it's going to be V plus Z. That's what an element in the quotient looks like. Okay, and you simply define that to be P of V. Okay. So then V naught with the seminorms P naught, where P runs through P, all right? So for each P, I do this construction of finding a P naught. Okay, seminorms is Hausdorff. And this is a natural way of starting with a non-Hausdorff locally convex space and building a Hausdorff one. Okay, so does that make sense?
Yep.
Okay, good. Okay, so that's Hausdorff. Good. So having talked about that, we're going to, like I said, assume that we're always going to be talking about Hausdorff spaces. There'll be times when we won't, and one of the only times that we won't is going to be coming up soon. All right. So the next topic is going to be um, subspaces and products. Okay. All right. Um, so whoops, let V O be an LCS. Okay, so again, it's not necessarily important for what I'm talking about right now, but it's Hausdorff. Okay, so if U is a subspace of V, then U inherits a topology from V by um, by saying that, and this is the use. So if you're given any topological space and a subset of that topological space is a natural way of inducing a topology on the subset, and so that's what I'm talking about here. It's what's called the induced topology, sometimes also called the relative topology or the subspace topology. Okay, and that topology is defined like this. Okay, by saying that O in U is open if there exists an, sorry, my open set. That's not the O I use for open sets. That's the O I use for open sets. Okay. Um, so there exists an O prime, which is open in the original topology of V, like this, okay, such that O is U intersect O prime. Okay, so that's how you define the relative topology. Is a set's open when it's the intersection of your subset with an open set in the big space. All right, so this is the induced relative. Sometimes it's called relative, sometimes called subspace topology. Okay, induced, sorry, topology. Okay, so this is more of a construction from topology than from locally convex spaces. So what's locally convex about this is that uh, uh, the induced topology is also locally convex. Okay, and that's really a consequence of the fact that um, if if you have a zero base of V, that you can choose a zero base consisting of absorbing disks, right? So absorbing convex balanced subsets, and the intersection of an absorbing disk in V with a subspace U is an absorbing disk in U. That's a very easy thing to check. Okay, so that's the reason why the induced topology on a subspace is locally convex. All right. Um, and so it is the coarsest, right? So when you talk about topologies, you can talk about them being coarser or finer or weaker or stronger. And so basically, if you have two topologies, you can't always compare the open sets. If you have two topologies, that's not always the case. that one collection of open sets is contained in the other one. That may not be true. And if that is true, you say that they're comparable. Okay. And so coarsest is a thing that you can say about two comparable topologies. So one topology is coarser than another one when it's open, when the open sets for the coarser one are contained in the open sets of the finer one. Okay, so the induced topology is the coarsest topology for U, such that the inclusion mapping iota U from U into V is continuous. Okay, so let's verify that just for fun. Okay, so first we should verify that the induced topology has this property that the inclusion map is continuous. Okay, so first let's show that the inclusion map is continuous. If U has the induced topology. All right. So what do you need to do to show that it's continuous is you take an open set in V, and you need to show that its preimage in U is open. That's not I, that's an iota. Okay, so if you take a subset of V and you take its preimage under the inclusion, well, this is exactly, if you think about what all the symbols mean, it's exactly U intersect O. Okay, so that these things are the definition of open sets in U, in the induced topology. All right. So the inclusion map is continuous, and so now you need to show that it's the coarsest topology for which that's true. So second, show that if, let's say, O prime is a topology for U such that the inclusion map is continuous, then O prime is contained in the induced topology. Sorry, it's the coarsest, so the other way around. It contains the induced topology. Okay. All right. So what we need to have then, so for this to be to see this, so we have if O in V is open. Sorry, not that O, I apologize. And sorry, up here too. I'm sorry, I got my O's mixed up. It's very confusing. That O. Okay. Okay. So if I have an open set like this, okay, then I know that this set has to be open in V. Sorry, in U. Okay, but again, this is simply U intersect O, okay, is open in the topology O prime. Because I'm assuming that the inclusion map is continuous. Okay. Okay, but this exactly means, so thus, um, this, okay, but this set is open in the induced topology. Okay. And so that shows, what this means is that every set which looks like this for an open subset of V, that must be an element of this topology. And so this shows that the induced topology is contained in O prime. And so the induced topology is the coarsest topology for which the inclusion map is continuous. So O prime contains the induced topology. Okay, does that make sense?
Yep.
Okay, good. All right. All right, so that's subspaces. Right, so it's not always true that you're working with subspaces that have the induced topology. Sometimes, for whatever reasons, subspaces might have a different topology than the induced topology, and that's important to keep track of. But the induced topology is an important one, and often we will make use of that one, but not always. Okay, products.
Do you have an example, like a quick example of an instance where we
Well,
might
you
not
can
use?
yeah, um I can give you an example. I don't know how insightful it's going to be. Um uh we know that if P is greater than Q, and Q is something between 1 and infinity. So what's true is, so we talked about these spaces of functions that are integrable, 0, 1, let's say. And let's just make them real valued. And so let's see here. So the inclusion goes this way. Okay, so that's true, and it's relatively easy to verify. Okay, so this is a subspace of that, but the topology on here induced from this is not the same as the topology on there. So there's an example. Like I said, again, I'm not sure that's awfully insightful. It's insightful if you know a bit about this stuff. Okay,
Okay.
so sorry, let me just finish one thing. So what is true is that the inclusion from here into here, it's continuous, but the topology here is not the coarsest one for which that mapping is continuous. Yeah.
Yep, that's fine.
Oh,
Thanks.
okay, good. Yeah. Okay. Um, okay. Right, products. So it's a homework question to talk about products in the product topology. So I'm not going to sort of uh, give that away here. So in the homework. To define, and by define I mean Google it. The product topology or family as topological spaces. So for topological spaces, let's say SA, OA, A. So an arbitrary collection of topological spaces. Okay. All right, so I'm not going to redefine that here. So this can be done, of course, for locally convex spaces. Because they're just topological spaces. Okay, and the product topology is always also locally convex. Okay, and moreover, if we denote by projection, PR, okay, so let me do it in general for general topological spaces, and the same is true for locally convex ones. So if we take our product of the SA prime, so we have then a mapping which goes from the product into SA. Oh, good, my dog has come to visit me. Sorry about that. I thought I prohibited that from happening. So in fact, I'm going to send my dog back upstairs. So I will be back in about 30 seconds. Sorry about that. She will annoy us if I don't get rid of her. Right, so we have the projection, which from the product of the SAs to, well, sorry, the product of the SA primes into SA, and it takes collection of things in the an element of the product, which an element of the product is just a family of elements of each product, and maps it to XA. Okay, so if we denote the product like so, then the product topology is the coarsest topology. And so this is, it's meant to be a theme because we saw another example of a coarsest topology above. Okay, so it's the coarsest topology. Oh, sorry, I see something in the chat. I don't know if that was half an hour ago or. Oh, okay. It should be. Did you have access to the on cue page? If you have access to the on cue page, it should be on the on cue page. If you're, I think, Bianca, you do have access to the on cue page. So if you can't find it, let me know and I'll send you the link to it. Yeah. So the assignment should be there. Okay. So the product topology is the coarsest topology, such that PRA is continuous for each A. Okay, that's one way of defining the product topology. And in fact, if you spend a moment thinking about it, this definition or this characterization um, of the product topology here um, can be used to give a more explicit characterization of what the product topology looks like. Okay. All right. And so both of these topologies, the induced topology and the product topology, are examples of what are called final topologies. Okay, so these are examples of final topologies. And I'm not going to define in general what a final topology is. Yeah, but I'll draw some pictures and you'll see that it's representative of the situations above. So the idea is that you have some set, let's call it X. Okay, so X has no topology at this point. Okay. And but what I do have is I have a bunch of mappings, let's say FA, into spaces with topologies, let's say SAOA. Okay. All right, so and so I have a little diagram like this for every A in some collection of indices, capital A. Okay, and then the final topology will be the coarsest topology on X, so that each of these FAs is continuous. Okay, and so for the product topology, these are the projections, and so and for the induced topology, there's only one of these mappings, and it's the inclusion mapping from U into V. Okay, and so why are final topologies um, sometimes why is this final property interesting? Well, what it allows you to do is it allows you to say, let's suppose that we're given another topological space, let's say T, um, with a topology O T, like so. Okay. And I want to know, is a mapping from T into X with the initial topology, okay, so the coarsest topology for which each of these FAs is continuous, is a mapping from T into X with its final topology continuous, right? So that's the question that I want to answer, okay? Well, the way you can check that is you can just by, let's call this map maybe G for the time being. And so I have a map here, which is FA composed with G. Okay. And so in fact, it uniquely characterizes the final topology. And so the final topology is uniquely characterized by the fact that G is continuous if and only if each of these is continuous. Okay, so sometimes it's easy to check this. Okay, so for example, for the product topology, all you need to do is check whether so maybe let me draw the picture for the product topology because I think it's interesting enough to single it out. All right, so let me redraw the picture above for the product topology. Okay, so I have some mapping into the product. Again, I'll call it G. And now I have the product of pi A prime. Okay, and then I have these projections. And I have here SA. All right, and so then the map here is projection composed with G. Right. So what this tells you is that if you want to compute whether the mapping into the product is continuous, where this thing has the product topology, all you need to do is just take the components of the mapping G in each element of the product and check whether those are continuous. Okay? And sometimes that's very easy to do. Okay. That's products. Okay, so subspaces and products. There's also quotients, and I'm not going to talk about quotients because I'm not sure that I will ever make use of them. Not that they're not particularly hard to talk about, but I'm not sure I'm going to make use of it, so I'm not going to talk about it. And if I do need to make use of them, then I will talk about them. All right. So the next subject is convergence and completeness. Okay. All right, so first, convergence. So you were familiar with the notion of a convergent sequence. Um, for general topological spaces, um, sequences do not adequately characterize convergence in those topologies. And what do I mean by that? So you have this, for example, in elementary analysis, you would have learned that a function, let's say f from, in elementary analysis, it's something like this. Okay, so f is continuous if and only if uh, so I'm being a little precise here because we're not really talking about this. I'm just recalling something from your past, right? So if you have a sequence xj that converges to some limit, and that's what that limit is, okay, then the function values also converge. Okay, so you would have learned that in your elementary analysis course. Um, but for general topological spaces, not just nice ones like the Euclidean spaces that I'm talking about here, for general topological spaces, sequences do not suffice to characterize things like continuity in terms of things like this. Okay, so you have to talk about not sequences, but more general things. Okay, so let me tell you what those more general things are. So first of all, um, a partially ordered set. Okay, so what we're going to talk about now is when you talk about a sequence, it's being indexed by a set of positive integers, which have an order, right? And that order is implied here when you're taking this limit. So j is getting larger and larger. And so there's an order there. And so you want to generalize that idea of that order property of z. And so a partial order, so a partially ordered set. Let's say I with a partial order like that. That's a terrible looking symbol, so let me redraw it. Okay, so that's like a less than or equal to, but it's got it's a curvy less than or equal to. In LaTeX, that's like that. Okay, so a partially ordered set, and so partially ordered set just the partial order gives you a way of comparing elements in the set, and the idea is you say that one thing is larger than another. That's what a partial order allows you to do. Okay, and so it should have the property that every element in the set is greater than or equal to itself, and if A is B is greater than A and C is greater than B, then C is greater than A. So that's what a partial order does. Okay, just like the natural order on the integers, except partially ordered sets can be more complex. All right, so a partially ordered set is called a directed set. If given let's say, indices I1, I2 in I, there exists some other thing, I3 in I, which is greater than both I1 and I2. Okay. And so the idea is in a directed set, no matter how large in some way, I choose I1 and I2, there's always going to be something larger than both of them. Okay. You can end up in partially ordered sets where you kind of go off on little branches of the partial order, and then um, maybe it starts to separate. So there might not be an I3 which is comparable to both I1 and I2. So a directed set is there's something larger and comparable to both I1 and I2. That's the idea of a directed set. All right. So then a net is a family. So a net in a set X is a family of points in X indexed by I. It's just that. So you write it like this. Okay, and so I should say, I'm sorry, I'm being a little bit sloppy here. I apologize. So I have a directed set I. Okay, and so let me, rather than rewrite everything, I'll just say here I is a directed set. I should have said that at the beginning of this little sentence. Okay, so I start with a directed set, and then a net is simply a collection of elements indexed by the thing. It's like a sequence. Okay, so a collection indexed by the terms in the directed set. All right, so it's a generalization of a sequence. Okay. All right. So now, if S O is a topological space, right, a net Xi converges to X in S if for any neighborhood O of X, there exists, okay, so what's the usual definition of convergence? It's that there exists, let's say, a capital N, so that Xj is in O for J larger than N. All right, so it's the net analog of that. So if you think about it for a second, the definition has to be this. Okay, so there exists some value of the index, and I'll just write that as I naught, such that Xi is in O for i's greater than I naught. So I naught less than or equal to I. Okay, so that's the adaptation of um, um, sequences to more general things, where the index set is replaced with a general directed set rather than the set of integers. Okay, so then fact, and again, this is relatively easy to check. Okay, you just have to choose the right um, partially ordered set to do things here. And so fact, F from, let's say, topological space S to, with its topology OS, to topological space T with its topology OT is continuous if and only if for any net xi converging to x in S. Okay, and so we write, so I should say here, if the net converges to x, we're going to write the limit of I in I x I equals x. Okay, so that's the notation that we're going to use for limits of nets. Okay. And so I'm going to use that notation here. All right, and so it's going to be the obvious thing. It's going to be f of the limit like so. Okay, so uh, um, what's true is if you just, so sequences are examples of nets. And so, for example, if you have a sequence in the normal way that converges to an x, then this statement is still true with the normal limits for sequences. Okay, so if it's continuous, then the normal sequence statement still holds. Okay, but what's not true is that if the normal sequence statement holds, and the normal sequence statement, of course, is this one. Okay, that is not enough in general to guarantee that the function is continuous. Okay, when you're talking about more complicated topological spaces than just, say, Euclidean space. Okay, does that, I mean, you know, um, you have to spend a few minutes, and then there's some information about nets in the course text, and there's also more information about nets um, in the background topology section. So if you want to find some things out about nets, then do that. We're not very often going to make use of nets, but I'm going to make use of them right now to define the notion of completeness. All right. Okay. All right, so let's make a definition. And now we're going to be talking not about topological spaces, but locally convex topological spaces. Okay. All right, so we're talking about completeness, and completeness is not a notion that you can talk about for arbitrary topological spaces. Um, it requires additional structure than just a topology, and that structure is called a uniformity. I talked about it a little bit before. And if you want to see stuff about uniform spaces, that's in the topology background section. Okay, but so locally convex spaces are examples of uniform spaces, so you can talk about completeness for them. So let me proceed to do that. Um, and heuristically, the notion of completeness, and so one of the homework problems is talking about completeness in normed vector spaces. So the idea there was to get you kind of the juices flowing about completeness in that setting. So that's what we're going to talk about now is an adaptation of that to not just norm spaces, but general locally convex spaces. All right. So let V O be a locally convex space, and let Xi be a net. Okay, so as soon as I write net, it's always implied that I is a directed set. Okay, that's why I forgot to mention that up here. Right, so whenever you write this thing down and you say that that's a net, that automatically means you're assuming that that's a directed set. Okay. All right, so you have a net. Okay, um, um, so we've already talked about convergence of nets. Okay, up here. Okay, and that definition of convergence applies to locally convex spaces just as well as locally convex spaces. But I'll sort of just put a placeholder here for that. And let me not use X, let me use Vi. Converges to V. Okay, and so the definition of convergence is the same as above. Sort of for every neighborhood of V, there's an I naught. Okay, so the definition is exactly the same. The new thing I want to talk about is what it means for a net to be Cauchy. If for any zero neighborhood, O, okay, so with zero neighborhood just again means a neighborhood of zero. So for any zero neighborhood O, there exists a sufficiently large value of the index, I naught, such that VI1 minus VI2 is in O. Okay, so the idea is O is a neighborhood of zero. And so this condition means that VI1 and VI2 are close to each other. Okay, so that's true for I1 and I2 greater than I naught. Okay. So the idea of a Cauchy net, so convergent means that as you go off to infinity, okay, um, things get closer and closer to X in the sense that for any neighborhood, the tails in this directed set or in the net will lie within O. Okay, Cauchy means that the difference between large terms in this net, you know, generalization of sequence, are close to each other. Okay, so the terms and the tails of these things get closer and closer to each other. That's what Cauchy means. Okay, and then 3, the O is complete if every Cauchy sequence converges. Okay. So you may say, why didn't I say if and only if every Cauchy sequence converges? Well, fact. Um, Convergent sequences are Cauchy. And let me prove that in, so you've probably seen this maybe for metric spaces, okay, and maybe for normed spaces. But let's see how that works for locally convex spaces. And let me do it using zero bases. All right. So, uh, so I have, suppose that the limit of I in I, Vi is equal to V. All right, so the net converges to V. All right. Okay, so I'm going to choose. So what I need to do is I need to show that for any zero neighborhood O, I can find a sufficiently large value of the index. Okay, and I'm going to use the fact that I have convergence. Okay, so here's how I'm going to do that. Um, let's let O be a zero neighborhood. Okay, so in the usual definition of Cauchy, this is like taking epsilon, right? So this is like saying let epsilon be positive. Okay. So since the thing is convergent, okay, let O prime be a zero neighborhood such that um, so uh, so first let me say that it is a disk, first of all. So it's convex. That's what I mostly care about. And I also, and it's balanced as well. Okay, so and because it's a zero neighborhood, it's absorbing. All right, so this is an absorbing disk. And you'll see why I need that in a second. But I know that I can always find a zero neighborhood, which is an absorbing disk, because the space is locally convex. Okay. So that's a disk and
Um,
yep.
Maybe the statement of the fact should say convergent nets are
Oh,
quotient.
but I apologize. Thank you. Yeah, appreciate it. Yeah. Yeah, thank you. Uh, okay. And the other thing I'm going to assume about O is that O prime plus O prime is contained in O. All right. And so again, if you remember back to our definition of linear topologies, one of the requirements of a linear topology was that given any zero neighborhood, we can find another zero neighborhood so that that's true. Okay. So you can always do that.
Also, just to check again, did you in the definition of a complete topological vector space, did
Yeah,
you
yeah, yeah.
mention?
I'm very sorry. Sorry. Yeah. Yeah, sorry about that. Thank you. Okay, did I do sequences anywhere else? Hopefully not. Okay. Okay. And so I'm going to find an O prime, which is an absorbing disk, and satisfies this property. Okay, and the properties of locally convex spaces ensure that I can do that. Okay, so then. Okay, so what I need is I want to check, so then choose, right? So in the definition of Cauchy, I need to find an I naught. Okay, so here's how I'm going to choose my I naught, such that, um, uh, such that V minus Vi is contained, is in O prime for I naught, for I greater than I naught. Okay, and that comes from convergence. Okay, so I know that the net converges to V. Okay, and I know that every neighborhood of V is a translation to V of a zero neighborhood. Okay, O prime. Okay, and so convergence to V means that I can find a zero neighborhood so that that's true. Okay, so then Vi1 minus Vi2 is Vi1 minus Vi naught minus Vi2 minus Vi naught. Okay, so that's obviously true. Okay, and this is going to be in. All right, so what do I know? And here I'm taking I naught, I1 and I2 to be greater than I naught. Okay, so I know therefore that this is in, oh, oh, sorry, V, not V, I naught, um, V. Okay. Right, so I know by this property that if I choose I1 to be greater than I naught, this is going to be an O prime. And similarly, this is going to be an O prime. Okay, so this is in O prime, and this is in O prime. Okay, and because I have assumed that O prime plus O prime is contained in O, that implies that all of this is contained in O. Okay, does that make sense? All right, so
Yeah,
if look back at the standard proof of the corresponding fact that convergent sequences are Cauchy for metric spaces or norm spaces, it looks just like this, except I'm replacing epsilons with neighborhoods. Okay.
very optimal.
Yeah, it's nice, and it's sort of more geometric than the sort of than the things using norms and metrics and stuff. Okay. Um, so what's the easiest way to check? So I've shown you here how to use the definitions in kind of I think a very slick way. But sometimes it's more practical to use semi-norms. Okay. And so a net converges to V if and only if the limit of P of V minus VI is equal to 0 for every continuous seminorm P. Okay, so that's how you check convergence of a sequence using seminorms. Is you fix a seminorm, okay, then you just check whether in that seminorm this thing goes to 0. Okay, and similarly, Cauchy. If, okay, so let me um, um, give an epsilon-y version of Cauchy. So if and only if, okay, um, for every epsilon and every continuous seminorm P, okay, there exists an I naught such that, so I think you know what's coming, right? Such that P of VI1 minus VI2 is less than epsilon for every I1 and I2 greater than I naught. Okay. You okay with that?
Yep.
And to check both of these statements, it's easy. And the reason it's easy is because, as we emphasized last time, there's this simple correspondence between semi-norms and zero neighborhoods and absorbing disks. Okay? All right. So these statements are relatively easy to prove. Okay. Next topic.
Sorry, just
Yep.
one question.
Yep.
So, can it be shown that your definition of completeness for a topological vector space, if you apply that to a norm space, it just corresponds to the sequential definition?
It better.
Yeah, I mean
And
that's
and so therefore that's just my sort of belligerent way of saying yes.
yeah, yeah.
So,
Okay.
and then that's easy. So first of all, for a norm space, you don't need nets. Okay, so and so okay, there's a little bit of work to do there to show that sequences are enough, right?
Yeah.
Um, and then, but then once you have that, then this condition, um, um, you know, so now your norm space, its topology is defined by a single norm. And so, you just need this to be true for the norm.
Right. Okay.
Yeah. Okay. All right. So continuous linear and multilinear maps, right? So we have um, so let's sorry, U and V and let's say U1 up to UK. These are all F vector spaces. Okay, so let me not think about topology for just a second. All right, so then HOM F of U V is just linear maps from U to V. Mm. And similarly, HOM F U1 UK, and so there's a nice semicolon there, nice semicolon here. V is multilinear maps from the product. Okay, so multilinear means um, if I fix all of the arguments, except one, if that one is free, then it's linear in that argument. Okay, so multilinear means linear in each argument. Okay, so mostly we're going to be concerned with bilinear things, but occasionally we'll see multilinear things that have more entries than just two. Okay, so the standard or classical example of a multilinear map that everyone's familiar with is an inner product on a real vector space. That's multilinear. And so, by the way, an inner product on a complex vector space is not multilinear. Okay. All right. And so L, Q, V are the continuous ones. L, U1. And I'll sometimes write LF, just like I write HOMF. So these ones are continuous. All right. Um, so we also have the notion of a bounded linear map. Okay, so a mapping, let's say A. Actually, I think I usually denote these with a phi in HOM U V is bounded if A of B is bounded for every bounded B. So it maps bounded sets to bounded sets. We talked about bounded sets in locally convex spaces last time. Okay. And so again, if you're familiar with the theory of normed spaces, you'll know that bounded and continuous are the same. Okay. That's not true for locally convex spaces. What is true is that continuous linear maps are bounded. Okay. So if you have a continuous, so let's see if I can prove that. So let B in U be bounded, and I need to show that its image is bounded. Okay. All right. So okay. So therefore okay, so I need to show that its image is bounded, and so that means that I need to show that the image is absorbed by any neighborhood in V. Okay, so let's let O be a zero neighborhood in V. Okay, so since since phi is continuous, the preimage of O is a zero neighborhood in U. Okay. Okay, so because B is bounded, I know that that B can be absorbed by this zero neighborhood phi inverse of O. So since B is bounded, there exists an R positive such that B is contained in alpha the inverse of O for alpha greater than R. Right? That's what it means to be bounded. It means it can be absorbed by any zero neighborhood. Okay, so then phi of B, okay, is contained in alpha phi of phi inverse of O, which is contained in alpha O for every alpha greater than R, and therefore phi of B is bounded. Okay, because again, I've started with an arbitrary zero neighborhood O in V, okay, and I've found a capital R so that if the modulus of alpha is greater than R, then the image of B is absorbed by O, okay? Okay, so in general, bounded linear maps are not continuous. Okay, so you know that that's true for normed spaces. I assume most of you at least have seen that fact that for normed spaces, bounded and continuous are the same. So the example would have to come from something not normed. Okay, so the example is going to be kind of, so the example is actually not that complicated, but it's a little bit beyond what we're able to do right now. Okay. Um, Uh, okay, I think that's all I'll say about these. And if there's any other features of continuous linear and multilinear maps that we need, I'll um, introduce those as we go along. Okay. All right. Completion. So every LCS admits so every LCS, oopsie, didn't want to grab that. Okay, so every LCS VO admits a completion VO with bars over them. Okay, and what that means is, so that is VO is a complete LCS. Okay, and there exists an injective linear mapping iota V going from V into its completion such that V is the closure of V, or V bar is the closure of V. And so what that means is that for every point in V bar, okay, so what does closure mean? So closure means the set of limit points, right? So you want to take all of the sequences, if you're thinking about elementary topology, all of the sequences in V, you want to take their limit points, which may or may not be in V. Okay, but those will be the things which will be in V bar. But we have to do that for nets. Okay, so what this means is that for every point in V bar, there's a net in V that converges to it. Okay, so that's what closure here means. Um, uh, so okay, so here's what I'm going to do. I'm going to give a quick and dirty construction of the completion because I think it's fun and interesting, and really shows that the theory of locally convex spaces has some meat to it. But it's going to take me more than 5 minutes. All right. So if you let me just say, if you miss this and you're prepared to accept this fact at face value and not see any sort of explanation for it, you can leave now and I won't hold it against you much. Um, but if you want to see how you build the completion, stick around. Okay, so here's how you do it. All right, so first you choose. Okay, so um, constructing the completion. Okay, so you choose a continuous semi-norm P, and you work with just a single semi-norm P for a few moments. Okay. And what you do is you consider the LCS, um, whose topology is just generated by P, the single seminorm P. So that will not generally be Hausdorff. Okay. Um, okay, so what that means is we're going to work with the what we have is a semi-norm space. So we have a semi-norm space, VP. Okay, so like a norm space, except the norm is just a semi-norm. Okay. All right, so then what we do is we we build the completion of this space in the usual way, and I'm not going to assume you know what the usual way is, so I'll tell you how to build a completion for this space. Okay. If you've seen how to build completions of norm spaces, then you'll know how to do this. Um, if not, then I'm telling you. So we build a completion, which I'll denote as that of VP um, as follows. Okay. So let CS of V be the set of all Cauchy sequences. Okay. All right, so this is some gigantic collection of things, right? So, a set of all Cauchy sequences, a huge collection of objects. Okay. So we're going to call two Cauchy sequences. Okay. So I don't mean Cauchy sequences, apologies. Actually, no, sorry. I cancel, I overrule my apology and I'm not apologizing. I mean sequences, not nets, because I'm working with a semi-norm space. Okay, so call two sequences in V, two Cauchy sequences. Let's say U and V, equivalent if for any epsilon positive, there exists an N such that P of uj minus vj is less than epsilon for j greater than or equal to n. Okay. So you have these two Cauchy sequences, and so what we know is that these are Cauchy sequences, so that as j gets large, the terms in the sequence gets closer and closer, and similarly for v. But what I know is that they're equivalent. I'm going to call them equivalent, and so that's a definition. Okay. When not only do the tails get close to one another as j gets large, but the tails of the two sequences get closer and closer together. Okay. Right. So you should think of a Cauchy sequence as a sequence that's trying to converge, right? So the terms are getting closer and closer, so it's kind of bunching up, but the limit doesn't exist. Okay, and so this is the intuition here is this condition is saying that the two Cauchy sequences, each of which are trying to converge to the same thing. That's the intuition. Okay. Then define V bar to be the set of equivalence classes of Cauchy sequences. Okay. All right. And so the idea is that each point in V bar is an equivalence class of Cauchy sequences. So it's like all of the Cauchy sequences that are trying to converge to the same thing. Okay, that's what an element of V bar is. All right. So it's not a vector, but it's an equivalence class of Cauchy sequences. All right. Okay. Um, okay, good. So we can show. All right, so we need to show, and you can show, and I'm not going to do. So if you sort of do all of the little gory details in this proof, it fills out like 7 pages, and it's just elementary computations. Okay, so there's nothing really very hard about this. So one of the things that you can show is you can show that V bar is a well-defined. So it's a vector space. Let me just say it that way. Okay. So what that means is, for example, you have to show that if you have two equivalent Cauchy sequences, then the sum of those Cauchy sequences um, um, is well defined. Okay, so um, it's independent of the equivalence class. Okay, and similarly for scalar multiples. All right, so there's just some messy, simple stuff to go to show that. Okay, so this is a vector space. Okay, so define a norm. So this will actually be a norm, not a semi-norm. P bar on V bar by P. Okay, so bar. Okay, so that's going to take an equivalence class of Cauchy sequences. All right, so I'm going to choose a Cauchy sequence, Vj, and I have the equivalence class of that Cauchy sequence. Okay. And this is simply going to be the limit as j goes to infinity, p of vj. Okay. All right, so you have some work to do here again. So you need to show that this limit is independent of the representative of the equivalence class that you choose. You have to show that this converges, but it converges because this thing is a Cauchy sequence. Okay. And then you have to show that it satisfies the properties of a norm. Okay, so why does this turn out to be a norm and not a semi-norm? Well, that goes back to the very, very beginning when we talked about Hausdorffness. And we talked about the fact that if you had just a space with um, a space with a single norm, P, or semi-norm P, and you wanted to build a Hausdorff space out of that, well, you quotient by the set of all vectors for which P is equal to 0. Okay. But that quotienting gets done by this equivalence relation here. Okay? And so what we've done then is we've arrived at the following thing. For every and so sorry, let me just do this. I have a feeling I'm going to have to move that down even further. Okay. All right. So we have this thing, and so there's more that you need to do. Okay. So define this, right? So in my definition of completion here, I had a mapping which went from V into the completion. So I need to define that mapping. Okay, so this goes from V into its completion. Okay. And what's that mapping going to be? So that mapping is going to take the okay, so it's going to take a point in V, okay, in V, and it's going to map it to, okay, so it's going to be a point in V bar, so it's going to be an equivalence class of Cauchy sequences. And what's the sequence going to be? The sequence is going to be the constant sequence. So the equivalence class of the constant sequence V, 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 and so on. Okay, so that's the mapping from V into V bar. Okay. All right, so then you need to check. And so now there's a little bit of cleverness that's involved, but it's nothing too extreme. Okay, so we need to check that. Okay, so this mapping now, iota V, this mapping will definitely, so here I've asked that this mapping be injective. Okay, but I'm not doing the final step here. I'm not actually building the completion of V at this point. I'm still just building the completion of the semi-norm space. And it turns out that this mapping iota V is not injective. Okay. So but what is true is the following thing, is that the kernel, so if iota V was injective, then its kernel would be zero, but the kernel's not zero. Sorry. Okay. It's equal to this. It's equal to the set of all vectors which map to zero under P. Okay, so it's not injective. If P was already normed, then the kernel would be zero, but it's not. Okay, so you can check that. And then you can also check that this thing is complete. Okay, and so I have my punchline now, which I delivered too early. For every P, there exists a complete normed vector space V bar P bar. Okay, so that's the first part of the construction. Okay, so now let's take the set of all semi-norms. So sorry, I'm going to turn my focus back on so I don't get text messages and crap. So now we're going to take the set of all continuous semi-norms. And I'm going to partially order it. And I'm going to say that P1 is less than P2 if and only if the obvious thing holds. P1 of V is as real numbers now. So this, I can't draw that symbol very well with my hands. Okay, so that's how you partially order the semi-norms. Okay. So one then has a mapping V. Okay. So let me get the direction right. So So I'm going to talk out loud to myself here for a minute. So if P2 is larger, that means that its balls are smaller, and so the mapping is going to go from P2 into P1. Um, yeah, that's right. Okay, P2, P1. This is going to be a linear, continuous mapping from um, V with the P2 seminorm into V with the P1 seminorm. Okay? Just this property ensures that this is true. Okay, so you have a continuous linear mapping from this locally convex space into this locally convex space. Right? They're very simple locally convex spaces. They have topologies defined by single norms, single seminorms. Okay. Okay, so one has a mapping like this, if P1 is less than P2. All right, good. Okay, so now what do you do? So now the construction is really, in case it's not abstract enough, it gets even more abstract. Now, take the product. Um, and I'm taking the product over all of the continuous seminorms P. Okay. Um, and I'm going to go V bar P bar. Okay. So this is a product of complete normed vector spaces. Okay. So the product is complete. So it turns out, and this is not, you can use very easily see with this um, uh, semi-norm characterization of Cauchy and convergent, you can very easily see that any product of complete spaces is complete. Okay, so the product is complete. All right, so, and now, so that seems like a weird thing to do. Um, what we're going to do now isn't necessarily going to make it clear why that's the right thing to do, but I'm going to do it anyway. Okay, so we then define a subspace W of um, of the product. Okay, so this is going to be the set of all points in the product. Oh, sorry, I'm indexing things by P here. Sorry. So let me do it that way. P, 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 P. Okay. And I'm sorry. Up here, I should have been a little bit more careful. I should have labeled each of these things with a P. So the completions should depend on P. With the construction using a single seminorm, it didn't matter, but I need to run this now over all possible seminorms, so I'm going to do it this way. Sorry. Okay. P, P, P. Okay. All right, so it's going to be a subspace, and it's going to be defined by uh, the existence of these linear mappings when one P is larger than another P. Okay. So it's going to be that, okay, so let me get this right. Okay, so it's going to be phi of, so phi, okay, so it's going to take something in, so VP2 is equal to VP1, and it's the mapping P2 comma P1, right? So it's these mappings here, okay? Okay, if P um, 1 is less than or equal to P2, okay? I think I have a dirty screen, which that's why the picture's a little bit pixelated. Okay, so this is just going to be a subspace. So you can verify that it's a subspace, right? So if these conditions are satisfied for two vectors, it's satisfied for the sum, and similarly with scalar multiples, and that's just because of the linearity of this mapping. Okay, um, and so because so one can show that W is closed. Okay, and subspaces, sort of closed subspaces of complete spaces are complete. It's so the there's a fact coming from that you can easily show yourself, but I'm not going to prove that here. So there's a whole bunch of stuff here you need to prove. This is just another in the long list of things that you need to prove. Okay, but the point is, since W is a closed subspace of this complete space, okay, W is complete. Okay, um, and uh, so then what you have to show that W is a completion of V. Okay, so you have to find this linear mapping in the definition of completion, right? Okay, but that turns out is relatively straightforward because what you do is you use the fact that you've built here uh, these um, mappings here. Okay, so we have mappings from V into each of these. Okay, that comes from our initial construction of the completion for the semi-norm spaces. Um, then that gives you a mapping into the product, okay, because you have one into each component of the product, and so therefore you have a mapping into the product, and that mapping is continuous by the um, property that I showed way up here by this diagram, okay. All right, so that mapping from V into the product is continuous, okay? And then you show that this weird condition here, okay, ensures that when you map V into the product, that its image is actually, the closure of its image is W, okay? So that's a sketch of how you build the completion. And the only reason I really wanted you to wanted to sort of say that, even though it's definitely not necessarily something I expect you to understand all those steps of, is that I wanted to sort of make a point uh, that there's non-trivial things that you can do with locally convex spaces, and this is beginning to see some of that because this construction right here um, turns out this is what's called a projective limit. Right? So the space, what this says is that the completion is equal to this thing, which is what's known as a projective limit. Okay. Um, so this construction that I made here of a product in the subspace, that's a special case of a more general construction called a projective limit. And so, for example, it shows that the completion of every locally convex space is a projective limit of complete normed vector spaces. So that turns out to be a very interesting thing in and of itself. Okay, not necessarily something we're going to use, but again, just to sort of illustrate that locally convex spaces have some nice structure to them. Okay, so if you stuck with me for that extra 20 minutes, congratulations. I'm also happy to just stick around for a few more minutes if anybody wants to ask any questions. But other than that, the lecture's done.